RaymondLickorish. I'm going to say a few words about symmetries that knots can have in mathematics. Knots to a mathematician are in a piece of string with no ends, so the ends are joined together, and we often draw pictures of our knots on a blackboard, drawing where the string crosses over itself. Often we're interested in knots with a direction so that we can put an arrow on our knot. But of course, starting from the picture, and I'll try and draw the same picture, so I can go around this way or the other way, and one can immediately get a picture of what may or may not be a different knot by changing all the overcrossings to undercrossings. So that is the same picture as before, only I have changed every overcrossing to an undercrossing. And I can put my arrow on in the one way or in the other way. So this is possibly 4 knots. And here I've got my trefoil knot, and it's got its arrow on it, and we can point out this axis of symmetry. And you should be able to see that if you had this knot made of wire, say, and you rotated it through 180 degrees about the yellow axis, the wire actually takes up the same position as before. The only difference is that the arrow has obviously been rotated through 180 degrees. The knot with the arrow going one way is equivalent to the knot with the arrow going the other way. Now here is the 4-crossing knot, and it too possesses the same property. You can see the white knot, and there's the yellow axis going through, meeting the knot at 2 points. If I rotate through 180 degrees about that axis, and if I draw on it slightly better, the white curve would go exactly to itself, and you can see all the crossings are made so that works, but the arrow would reverse. Here's another picture of the 4-crossing knot. It's the same knot that we got over here. If one rotates the plane about this point here through 180 degrees, the whole thing maneuvers over to this other picture where the green arrow becomes an arrow going up like that. Every crossing has been changed, so whereas I had an overcrossing here, I have an undercrossing there, and similarly for all the others. But we just noted over here that we can change arrows at will by rotating about a different axis. The upshot of that is that for this 4-crossing knot, there is in fact only 1 knot, and it doesn't matter how I put the arrow on or how I change the crossings, I've always got the same knot because I can maneuver one picture to the other one. Over here, however, we have the knot 933, and that really does give 4 different knots. Now, it's one thing to convince you that I can do something, because all I have to do is to do it. To prove that you can't do something is not really sufficient to try, get stuck, fail, and say it can't be done. One needs a mathematical invariant. One way of wondering about whether a knot and its reflection are the same is to think about polynomial invariance. Now, on this nice little transparency here, I've written out the polynomial that turns up for the 3-crossing knot, and it's to be seen along the top. Minus 2l squared minus l to the 4th plus l squared m squared. Now I'm going to turn the transparency over, and that in this particular case will have the effect of changing all the crossings from overcrossings to undercrossing. Watch that there is a strand going over as it goes up the top left there, and we turn it over, and there it is, it's going under as it goes up the left-hand side. And underneath is written what the polynomial works out to be. Those polynomials are different, so the knots are different. So that's at least a way, a fairly modern way, of proving that my right-hand trefoil and my left-hand trefoil are distinct. So when I drew the 3-crossing knot, the trefoil knot here, there weren't 4 knots, but there were 2.